Let's look at f. Notice in f we have 3 square roots of 11 minus 2 square roots of 13. The difference here with 11 and the 13 is I would like to turn them into the same type of root so that we have like terms, but the problem is 11 and 13 cannot be broken down. They're both prime. So I can't turn out the square root of 11 into anything, and I can't turn the square root of 13 into anything, so I'm stuck. So I can't ever make these be like terms. So this is as far as it can go. We'll go ahead and say that this is already simplified in f. You can't do anything. You can't turn these into like terms in any way, because you can't break down 11 and you can't break down 13. Let's look at G. In problem G, we have the square root of 18k minus the square root of 72k. Now the hope is that we can break down the 18 and the 72 so that they will be like terms. The 18 can be broken down as 9 times 2. So that when we take the square root of 9, it will come out as a 3. But you'll be stuck with that 2 and the k inside of the root because you can't take the square root of either one of those. Minus, so my goal now is with the 72, when I break that down, is that hopefully I end up with a 2 left over as well, like I did with the 18. Well, does that mean 2 goes into 72 at all? It does, 36 times. So that will work out perfectly, because when I take the square root of 36, it will come out as a 6, but just like before, I can't take the square root of the 2 or the k, so those will stay inside. So those will be like terms. So I've got 3 of these square roots of 2k and minus 6 of these square roots of 2k. Those are like terms because they both have a 2 and they both have a k on the inside of the square root. They match up. So this will give me negative 3 square roots of 2k. Look at h. On h, we've got 9 square roots of 27x squared minus 14 square roots of 108x squared plus 2 square roots of 48x squared. So on the 27 on this first root, I can only break that down into 9 times 3. I can take the square root of the 9. It will come out as a 3 to get multiplied by the 9 that was already there, which will give me a 27. But I'll be stuck with this other 3 inside of the square root. Also, I haven't even talked about this, the square root of the x squared. Because it's a square root, we will have that 2 goes into 2 once and will come out just evenly as an x. That's nice at least. Now I have to do the same thing with the 108. How does the 108 break down? Again, the hope is that I have a matching 3. Well, 3 goes into 108. Let's see how many times. 3 goes into 108. 36 times. So when I take the square root of 36, I get 6. That'll get multiplied by your 14. So it'll be 6 times 14, which is 84. So that's, be careful, that's a negative 84. And we'll be stuck with that 3 on the inside that we can't take the square root of. However, we again have a square root we can take the square root of. That will come out as just an x, just like before. Now this last piece is added. Let's see what's going on with this last piece. This last piece we have a 48. And again, the hope is that we can break that down into something that's going to have a 3 left over. So again, they'll be like terms again, hopefully. Well, 3 goes into 48 16 times, so I can take the square root of the 16. It will come out as a 4 times the 2 will give me 8, so that'll be a positive 8, with, again, the 3 left over on the inside. Just like before, I can take the square root of the x squared. It will come out as just an x. Now, let's look at the magicalness of the situation. Is we do have 3 matching like terms. They all have an x on the outside of the square root, and they all have a 3 on the inside of the square root. Because they all 3 match up with an x on the outside and a 3 on the inside, they're absolutely like terms. So then I can just add their numbers and subtract their numbers. We've got a 27 minus an 84 plus an 8. So that's all you have to worry about. So when you add the 27, the negative 84, and the positive 8, we get a negative 49 of what? All of these have an x and a square root of 3. So that is our final answer. Let's look at problem I. We're close here on this one. They're almost like terms. Notice we have a cube root, a 3 cube root of x squared y squared minus 2 times the cube root of 64x squared y squared. Notice they are almost like terms. The only difference between the two is that inside the cube root of the one on the right we have a 64. But what's wonderful is we can go ahead and take the cube root of 64. We just get a 4. And then we can take that 4 and multiply it by the 2 that was already out in front. And that will turn into an 8. Then all we'll have left inside is the x squared and the y squared inside of that cube root. The first piece doesn't even need to change. And now they are like terms. They both have an x squared and a y squared inside of their cube roots. So they're both cube roots with an x squared and a y squared inside, so they are like terms now. I can add and subtract normally. I've got a 3 minus an 8, which will give me now a negative 5. So negative 5 cube roots of these x squared y squareds. And that's my final answer. Let's look at J. J is very close as well. If we start out with J, we've got 2 fourth roots of m to the 9th p to the 6th minus 3m squared p, the fourth root of mp squared. So what we notice is that this first one has more stuff on the inside of its root. So there's some stuff we can do to simplify. So let's take a look at this first fourth root. Well, see if we can simplify it by dividing the 4, that is our root, into each one of the exponents. They don't divide in evenly, so some stuff will be on the inside, some stuff will be on the outside, but we just need to kind of tinker around with it. So let's go ahead and see. So if we divide the 4 into the 9 for the m's, let's see what happens for those m's. 4 goes into 9 2 times as 8 with 1 left over. The 2 m's came out and 1 m was left over on the inside. So on that first piece, we already had the 2 on the outside. What this is now telling me is I'm going to have 2 m's on the outside and 1 m on the inside of the fourth root. Okay, now let's do the same thing for the p's. Let's look at the p's. So that's a 4 and a 6 then. So with the p's, we're looking at 4 going into 6. Well, 4 divides into 6 once as 4 and leaves me with 2 left over. So 1 came out, divided out, and 2 were left over on the inside as my remainder. So that means 1 p is coming out of the root, and 2 are left over. That means a p squared is left over on the inside. Well, notice, miraculously enough, that matches up with the other p. So it has a negative 3m squared p and a 4th root of mp squared. Now notice these are like terms. Why are they like terms? Because both of them have an m squared p on the outside, and both of them have a 4th root with an mp squared on the inside, so they both have that 4th root of mp squared. So what's outside of the root matches up, the type of the root matches up, and what's inside the root matches up. So that's why they're like terms. That part will stay the same. Then I can just add and subtract the numbers normally, which is the 2 and the negative 3. Well, 2 and negative 3 is negative or negative 1. Remember, if it's a negative 1, I can go ahead and hide the 1 and just write the negative sign. So we'll leave it as negative, and that will leave the like part the same, the m squared p and the 4th root of mp squared. That's our final answer. So in conclusion, just like all of math, if we're adding or subtracting, we need to have like terms. That means we need to have matching roots. If we can't make them match by simplifying them, they aren't like terms and we can't add or subtract them. But if they are like terms, meaning whatever's inside the root and whatever's outside of the root and the type of root match, then we can add or subtract just the normal numbers. And whatever is the like part will stay the same.